Yes, sir. It is 4. Question number 4.
Question number 4. Okay, let me check once.
Week 5.
Yeah, let me check. Week 4 or week 5?
Week 5, sir.
Week 5.
Question number 4.
Mm-hmm. The Kuhn Tucker's one.
Yes, sir.
Okay, we'll be doing
I
this, I think.
Okay, I calculated x and y values.
Mm-hmm.
Many times I calculated no options are coming. How I am sure in week 6 question the
Mm.
same choices are given. One of the week 6 question, maybe some error in giving the options. If you see the week 6 assignment question,
Okay.
one of the assignment question is given the same option. That means question number 6. The same options are coming. That's why we got doubt. 702.9, 802.9, 710, 650.
Give me a minute.
Week 6, question 6. The same Kumtakar, I think.
Okay. That might be problem, I think.
Some error, but we lost the points. We don't know what to do
Yeah, you
because it
can
is a random.
raise a something
I
like.
raised the queries
Okay.
in Q&A. No one is answering in that.
Because
I
this
raised.
this assignment questions and all, no, this is not under me. So okay.
Yeah. Even another one also pointed out that same after I raised 2 3 queries, no one
Mm-hmm.
is answering from the beginning.
Wait,
Q&A is not active, sir.
wait,
Is not active.
is it?
Actually, I mentioned that in feedback also.
But this Q
Discussion.
and A, it should come to me also, I think. I mean, this.
I am okay. Okay, you are the only person TA.
No, there is one other person, but there should be one more person who is handling this assignment questions and all.
Okay, okay.
Wait, let me check. It should, like, I should get
Mm,
notification if you are raising queries. I am not getting any.
mm.
See, there are 4 5 things here.
Yes, sir.
I have not seen this. I didn't get any notification only.
Okay, might be you might not have joined. If you join, then only you will get notification. I hope so.
Oh, okay. I'll join. I'll join. Yeah. Fine. Okay, next time I'll get.
Okay. So please
Oh shit.
reevaluate and do something.
Okay, this re-evaluation is not under me. So if there is any
But
question
but
there where you have lost the point, you will be given it later, I think. Okay, I'll see with the this NPTEL
in
team.
some other courses they are doing, considering all these kind of errors, they are
Yeah,
either
yeah.
making this
The
0 mark question or something they are doing.
yeah. The last time I did, it was with me, but this
There must
time.
be some mechanism for this.
Oh, there were more questions. I have not seen this. Okay.
No problem, sir. I raised Tucker condition only that you have last class you explained. No
Oh,
problem.
we'll be discussing that today also. It's not no issue.
Okay. Okay. This week, some practice assignments are there. This week's
Sorry.
this week's content based.
Yeah. Week 6. Week 6
Yes,
will
sir.
be discussing, yes.
Okay, sir.
Yeah, some other one, someone other than you also posted, I think.
Yes, sir.
Uh, okay, okay. See, these questions and all are not with me, okay? So this
Okay,
is
sir.
being done by IT Guwahati people. Okay, I'll check that.
But but you can call forward this to them.
Yeah, yeah, I'll try to do that. Okay.
Only you are the point of contact for students.
Yeah, yeah.
So
Okay, okay, I'll try.
you can forward this to the team and please.
Okay, so there is one more question which has the same option. Yeah, that is there is some issue in the options in question number that
Yes, sir.
in
Some
week
error
5
maybe.
lectures. Yeah, 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 sure. I'll check that.
Okay, sir. Thank you, sir.
You'll get the point, don't worry. We'll start the session at 6:10. Okay, I'll write that.
Okay, sir.
Let others join. In,
Are you handling the session tomorrow also for problem solving?
no, tomorrow someone else is there, I think. Monday I used to take and Tuesday someone else.
Okay.
Guru Prem is taking, I guess.
I think last Tuesday you have handled.
No, no, last Monday only.
Monday.
Yeah.
Okay.
You joined, I think. Yeah, yeah, you
Yes,
joined.
sir. I joined
Hmm.
another person also. Sir, for final exam, how many questions will be asked, sir? Each carries 1 point or something like that, or based
No,
on the
mix will be there. 1 point will also be there. 2 points will also be there.
quantum of work, the points will be given.
Yes, yes.
Yeah. Any previous year question papers possible, sir, for us for
No,
practice?
no, no.
All courses are not giving previous year question.
Yeah, that is not possible.
Rough papers for rough work, they will give A4 sheets.
Yeah, they will give. They will give.
Calculator we can
Ca-
take.
calculator will be there in the system only.
We cannot bring
I'm not sure.
because sine and cos those
And
values.
that will be there in the calculator in
Okay, sir.
the question only.
Okay, sir.
We'll be starting this session at 6:10.
Okay, sir.
Sir, I have registered 3 courses.
Hmm.
In that, 2 courses are exam coming on the same day. Will they map for morning one exam, afternoon one exam, like that? Will they map for me or house?
Yeah, they should do that, but just in case you write a mail to the NPTEL team.
What is the mail ID, sir, for that?
Some IITM something is there.
In the contacts?
Yeah, it should be there in the contacts.
Sir, can you please send the mail, sir, mail ID for me?
Yeah,
No, mail ID.
I'll check
Mail
that
ID.
after the session.
Okay, sir.
Hmm. Okay, so let's start. Okay, hello everyone. So today we'll be discussing about the as the tutorial session for the week 6 lectures of the course, that is optimization methods for civil engineering. I'm Balram Sao. I'm the PMRFTA for this course. I'm doing PhD at Interdisciplinary Center for Water Research at IISc Bangalore. Okay, so before that, before moving on to the questions directly, let us see what we have learned. I hope you can see the screen. I think this is the one. Yeah. Oh, serene option. Okay, fine. Okay. So I hope you can see the screen. Okay. So what all we have. So first question is related to Cohn-Tucker's conditions only. So before that, we'll move to the explanation part. Let's see. So we are in the week 6 lectures of the course optimization methods for civil engineering. Okay, so what all we have learned till now. So last week we have seen about the quadratic approximation, how to do that and how to use that. Then we have also discussed about the optimization problem or the constrained optimization with equality constraint, right? So we have also done the unconstrained optimization, how to do that. Then we have moved to the constrained optimization with equality constraint. And then today we will be discussing that if there is any constraint which is not of equal to type, that is it can be less than equal to type or greater than equal to type, that is any inequality constraint are there, how to deal with those. So we'll be studying constraint optimization with inequality constraint. We'll be seeing the necessary conditions and whether it is a sufficient conditions or not, and so on. So till now what all we have seen. So we have seen unconstrained optimization, Then we have seen the constraint optimization or constraint problem, or let's say optimization problem with equality constraint. So remember, for this equality constraint we have used Lagrange's multiplier, right? Okay, so in the Lagrange's multiplier, what all condition was there? This was the necessary condition when we have the equality type constraint necessary conditions. So let's say when the optimization problem was something like, was that, let's say minimize fx subjected to some constraint, that is, let's say gx is equals to 0. Then what were the conditions? This necessary conditions. Can anyone tell me?
Dou L by dou X
Yeah,
equal to 0. Dou L by dou Y equal to 0. Sorry, X.
yeah. So this one, sorry, this one should be equals to 0, and why it became black, whatever, and del L of del lambda I
Dou lambda equal to 0.
0. So here we know that lambda j was the Lagrange's multiplier, and this j denotes the constraints. So let's say we have m number of constraints. Okay, so so g1x equals to 0, g2x equals to 0, sorry, and so on. So this will go to gm of x is equals to 0. So j will vary from I equals to, sorry, j equals to 0, sorry, not 0, 1 to
M.
correct. So 1 to m, and let's say in this capital X, this is a vector. So let's say we have multivariable function. We have the functions from x1 x2 till n. Okay, so this I varies from 1 to n. Okay, so what was the Lagrange's function? Okay, we can't do that. Lagrange's function, the function is something like L, let's say x and lambda is equals to f of x plus summation j equals to 1 to m lambda j gjx, right? I hope this was the one. Let me just week 5, I've explained it here somewhere. Yeah, here. So here L of x1 x2, so this was written as, right now this was written as x and this one was written as lambda. So x and lambda were the vectors, fx plus summation lambda 1 lambda I into gjx. We'll go to that directly. Okay, no, saved, right? Okay, so this one was the case when we have minimization function of fx. Okay, so similarly this one was for equality constraint. Now we have optimization problem with inequality constraint. Okay, so this inequality constraint means either less than type or maybe greater than type. Okay, so here also let's say we have to minimize fx such that or subjected to gj of x is less than or equals to 0, where this j varies from again 1 to m. Okay, so right for now what we'll do, we'll convert or transform this less than equal to type to equal to type. So for that what we'll do, for in this case we'll consider something like gjx plus yj square equals 0. Okay, so like this. Okay, and we'll write this as, let's say, capital gj of x. Okay, so how many number of constraint we have? We have m number of constraints, and again we have n number of variables, right? So here now we have one more variable, I mean y1 y2, one more vector, right? It's fine, right? You guys can hear, I hope. So we have one more vector which contains y1 y2 y3 y5 till number, how much it will be, till m, because we have m number of constraints and in that we are putting this yj, so we have m more number of variables. Okay, so now the Lagrange's multiplier, if I write, so this Lagrange's Cohen-Tucker condition will also come from this function itself, if we can see. Okay, I'll not go into detailed proof. Okay, so if we write Lagrange's function for those, it will be written as L of x, y and lambda is equals to f of x plus summation j equals to 1 to m lambda j into gj of x and y, right? Okay, so here also we have to write that gj of x and y, because here we have, so here x is what, x is a vector with x1 x2, let's say till xn. Lambda is what, lambda is lambda 1 lambda 2 till lambda of m, right? And y is,
Sir,
yes, y1 y2 till ym, yes.
sir, this plus yj square,
Mm-hmm.
even for less, it is common for less than equal inequality constraint and greater than.
No,
Greater than
no,
also we are adding.
for greater than we have, will do minus.
Okay,
Otherwise,
sir.
yeah, otherwise it will not be there, right?
Surplus.
Yeah. So let's say we
Mhm.
have something like 2 is, or
That consideration we have to keep in our
yeah, yeah,
mind.
yeah. Whenever
Okay,
this
sir.
minimization function, maximization function is there, if we have greater than equal to type and less than equal to type, so based on those combinations, you consider only one path. Okay, so as I said in the previous class also, that person to person they changes, but you will,
Yes.
and the basic thing or the basic formulation you need to keep in mind. Okay. Ah,
Okay, sir. Okay,
okay,
sir.
so what are the necessary conditions? The necessary condition is simply we have to find out the first order derivative and put it to 0. So necessary conditions will be, so now see, as we have one more vector, the necessary conditions will increase. First one will be del l del xi, this should be equals to 0. Then second one will be del l del lambda j, this should be put equal to 0. And third will be del l del yj should be equals to 0, because now we have introduced this term, that is yj, and from this we'll have different conditions. Okay, so these will lead to the Cohen-Tucker conditions. Okay, I'll go to the Cohen. So putting all those 0, and then if you like just do some maths, then what all we'll get this. First one will be del fx del xi plus summation j equals to 1 to m lambda j into del gjx divided by del xy is equals to 0, where I varies from 1 to n. Okay, next will be gj of x is equals to 0, where what happened, j belongs to j1, where j1 and j2 will come. Next is gj of x plus yj square should be equals to 0 when j belongs to, okay, so these are not the condition. I'll come to that because I need to explain this. So here j1 j1, this j1 are the active constraints. What are active constraints and all, I'll come. Okay, so let's say if the color, right, yeah, so let's say you have a function which is to be minimized and you have two constraints. One is let's say x is less than equals to 10, and another is let us say x is less than equals to 20. Okay, now if you see both this constraint, that is x is greater than or equals to, sorry, if x is less than or equals to 10, and this constraint, that is x is less than or equals to 20, even if this constraint was not given, this x less than equals to 20, it would have done the work, because x less than equals to 10 only means that it is less than equals to 20, right? So this constraint will act as redundant constraint, or let's say non-binding constraint. So this will be the non-active constraint. There are several names given in several books. Non-binding constraint, because it is not binding anyway, because x less than equals to 10, let's say this is the line when we have x is equals to 10. Now x less than equals to 10 means before this. Now we have x less than equals to 20, so even if we remove this, anyway we will be in this side only, right? So if we have two constraint, x less than equals to 20 and x less than equals to 10, then only this one will suffice. Okay, so this is not binding, this x less than equals to 20 is not binding, hence it is called non-active, non-binding constraint or non-active constraint. Okay, so we need to understand that which all are non-active sorry, active constraints, so that we can consider that in the Cohn-Tucker's condition. Okay, so if you see that one more condition will come, that is lambda. Okay, it is lambda j sorry, one is this, sorry, क्यों नहीं रहा है, क्या हुआ, अच्छा, yj equals 0, where j is equals to 1 to m. Okay, these active constraints and all are clear to everyone. If it is, I'll move then. So
Is it YJ? Are you sure,
no,
sir?
no, no, I'll come to this from this
Okay.
we'll have, because this is coming from this del L del yj equals 0. Okay, I don't remember, so I'll come from there. So
Okay,
so
sir.
for this, what we can have either yj is equals to 0 or lambda j should be equals to 0, right? Now as I was mentioning this active constraints and all, for that only we came to this. So if this lambda j is 0, okay, if lambda j is 0, this means what, that if you put lambda j in the Lagrange's function, what we will get, we'll get that the whole term to be 0. So this means that constraint will become non-active constraint. Okay, so in that case, if lambda j is 0, then in that case the constraint will become non-active constraint. Okay, for this, and if yj is equals to 0, this means what, the constraint is active, and hence we have to consider those constraint. Okay, so the optimality condition will be, or what all, so we have discussed that in the last class, right? I'll check it once, or else अरे धीरे आराम से पानी गिरेगा. Okay, so one will be GJX should, अरे कहाँ गया, there is some confusion I think. Okay, so with this, so if what I said, if lambda j is 0, then it will become non-negative. So this means what, lambda j should be what, so that we can have this active constraint, lambda j should be greater than equals to 0, right? So that will be one of the conditions. So I'll write it properly. So let's say if we are writing the Tucker's condition, so I'm writing only for the active constraint. So let's say we know the active constraint. Okay, so if lambda j is getting less than 0, this means what, that constraint is not active, right? So we'll write the condition del fx del xi plus summation j equals to 1 to m lambda j into, sorry, del gjx divided by del x of I should be equals to 0 for I given to 1 to n, right? Next will be lambda j into gj should be equals to 0, so that our second condition is followed. Next will be, this one will be for j is equals to 1 to n, and then gj, that is the constraint which is having inequality type, so this one will be less than equals to 0, that is 1 to n, and lambda j should be greater than equals to 0, otherwise it will be inactive constraint. So j is equals to 1 to n. So these four conditions are the Kuhn-Tucker's condition. Okay, so here lambda j greater than equals to 0, this only means that it is active constraint, because whatever constraint which is having less than 0 value, those will be discarded, because those are the inactive constraints. Okay, so these all will act as the necessary conditions which satisfies the let's say the local minima or the relative minima of f of x. Okay, and now, so what I said, this is the necessary condition, not the sufficient condition. So let's say if we have the constraints and the constraints are all convex, so we know now what is convex functions and all. So if we know that all the constraints that we have, that is the inequality constraints, those constraints are convex in nature, then these conditions only will become the sufficient conditions. So these conditions will become sufficient condition when so let's say if we have convex problems, then these conditions will act as sufficient condition, and this means what, we'll get the global optimum value or global minimum in this case, because we are doing for minimization function, right? So these will be the sufficient condition for the global minimum if fx is convex. Okay, now similarly if we are going for maximization function, right, if we are going for maximization function and all the constraints are concave in nature, then this one will the same conditions that we can see, plus minus no change. So when if we have maximization type and the constraints and all the whatever functions are there are concave in nature, in that case what will happen, this conditions will only act as the sufficient condition for finding out the global minimum, oh sorry, global maximum, in case of maximizing the um, optimization problem. Okay, is it clear?
Yes, sir. But one doubt.
Yeah.
What about the lambda value in case of maximization condition?
Lambda value, so if we are putting here, okay, I'll change the color once. So let's say if you have a maximization type, so what all changes will be there, this will change, this del fx del xi, this will become minus m2n lambda j gjx equals to del xi equals to 0, and other than that all will be same whatever we have, that is lambda j gj will be equals to 0. So this gj means gj of x. Okay, gj will be equals to 0, this one will be less than equals to 10, and this one will be greater than equals to 0. Okay, and this,
Lambda
so
value
this
will
n
lambda
mostly
value
it will
greater.
go to till p. This p is means how many active constraints are there. Okay, I am writing here n, so that let's say if we all the constraints are active constraint, then it will go till n. Now if let's say we have 5 constraint and out of these only 3 constraints are active, so in that case lambda j will be greater than 0 for 1 to 3, 1 to 3, because we have only 3 active constraints. Yeah, now you are saying something.
Sir, actually, I did maximization
Mm-hmm.
with dou f by dou x with a plus sign,
Okay.
but lambda j less than or equal to 0. That is that correct?
Okay, if
But
you
I
are
got the
considering
answer.
plus,
Like
it should work, because here in the last problem also, in the last tutorial also, if you would have gone with my whatever I have explained,
yes,
in that also
yes,
if you see I have given all the kind of in what case
yes, sir.
what it
All
will be.
pieces.
Yeah,
Yes, sir.
so in that case it will work, because anyway we are considering plus here in place of minus, right? So
Yes,
in
sir.
that case you can put it minus. Remember the gjx should be less than equals to 0 in that case.
Yes, sir.
Okay.
Gj less than 0 that I followed, but lambda j less than
Yeah,
0 for maximization.
less than equals to 0, but in that case it will be plus of summation j equals to 1 to m lambda j gjx del
Yes, sir.
xi equals to 0. Fine.
Yes, sir.
Okay, so this much is clear, right?
Clear, sir. Clear.
Okay, now let's say okay, so this is when only we have inequality type. Now we have equality type also, then this conductor condition only one thing will change. Let's say if both equality and inequality constraint are there, then let's say same, okay, I'll write it properly, otherwise it will be difficult. Is f of x, so here as I said that x is a vector considering all x1 x2 x3 till xn. As I am writing like this, I'll put transpose subjected to gjx less than equals to 0 for j equals to 1 to m, let's say. Okay, and other than this we have equality constraints also, right? So here, so I'll put this as k, where k goes from, let's say, 1 to p, let's say. Okay, then what will be the Cohen-Tucker's condition? Can anyone tell me? So it will be the same, just you will have this extra constraints. So it will be same only, that is del f x del xi plus summation j equals to 1 to m lambda j del gjx del xi plus summation k equals to 1 to m, sorry, p. So here let's say we'll put some other constant, let us say beta k, that will be x del xi equals to 0, and here I equals to 1 to n. Okay, next will be lambda j gj is equals to 0. That will come from del l del lambda equals to 0. Then we have gjx should be less than equals to 0. We have hk should be equals to 0, or hkx, let's say, and lambda j should be greater than equals to 0. For all this, j should be 1 to m and k should be 1 to p. Okay, so we can, let's say we have a mixed we have an optimization problem where we have both equality and inequality type. So this small change will be there in the Cohn-Tucker's condition. As I mentioned that if these Cohn-Tucker's conditions are the necessary conditions for the any optimization problem, not the sufficient conditions. So for sufficient condition, what we do in Lagrange's function also, those Lagrange's functions were for the act as the necessary condition. If we want to know the sufficient condition, what we'll do, we'll go to the higher order, that is the second order, let's say. So in that you uh, make the Hessian matrix and then you solve and you check the eigenvalues and all, right? So for that we go for the Hessian matrix. So in this this one will act as sufficient condition when, if, as we are doing for a minimization function with inequality time constraint, now if the function is convex in nature, then what will these conditions only will act as the sufficient condition for the problem. Okay, so we'll do some problems. Okay, so first question is for a non-linear optimization problem, and as we know that anyway we are mentioning convex function and all, so this optimization problem, even if it is non-linear or linear, we can solve it with these whatever we are doing right now. So with inequality constraint, the Cohn-Tucker conditions are the, so can you just tell me for a non-linear
Option B.
so see here it is mentioned non-linear optimization problem. So whatever we are doing right now, it can be linear, it can be non-linear, no issue. Okay, even if it is like very higher order non-linear, we can approximate it to quadratic function and then we can do the optimization whatever methods you want to use. So these Cohn-Tucker conditions are the necessary conditions to solve the optimization problem just mentioned. So B will be the option. Okay. Okay, we'll move to the next question. Who's calling here? Is that clear, everyone?
Yes, sir, it's
Okay.
clear.
Okay. So next question is, consider the following nonlinear optimization problem and find the value of z. So z is the optimization function, right? We have to maximize this. Oh, I think this is the same question. I think, yeah. Okay, fine. Subjected to this, x plus 2y should be less than equals to 10, x minus 3y should be less than equals to 9, and x and y should be greater than equals to 0. Okay, can you just solve same question only? I think same options are there, so
It's option A, 702.9.
yeah, I think that only come. So anyway, I have to do that because it will I have to put it in YouTube, so I have to put this. Okay, I'll do this, right? So let's say if that is the case, so we have to minimize this function, that is z is equals to 7x square. So let's say what we are doing, anyway we are, whatever we are doing is for minimization, so we'll just convert this and we'll write it as minimize, let's say z dash is equals to minus 7x square minus 6x minus 5y square. I just multiplied with minus 1 so that I can convert it to minimization function. Okay, and it is subjected to this, both are inequality constraints, so it's fine. less than type. So x plus 2y should be less than equals to 10 and x minus 3y should be less than equals to 9. So this one, first one is my, let's say g1x, and second one is my g2x, right? And given that x and y is greater than equals to 0. So now what we have to do, we have to write the let's say Lagrange's function will write, where should I write, L of x, y and lambda, let's say. Okay, so this one will written as f of x. So here f of x is was z dash, right? So we can write it as minus 7x square minus 6x minus 5y square, right? Plus lambda 1 into, here it was capital Gj, right? So we can write this x plus 2y less than equals to 10 as capital Gj of x of y, g1, let's say g1 of x. That one will be x plus 2y minus 10 plus, as I was doing, plus yj square, right? So plus y1 square, this equals to 0. So we'll write this, that is x plus 2y minus 10 plus y1 square. There will be one more term because we have to constrain it. One will be x minus 3y minus 9 plus y2 square equals to 0, because from this you'll get g2x is equals to what, x minus 3y minus 9 plus y2 square. This should be equals to 0, right? Why this is having a problem? Okay, fine. Okay, now you have to put all the functions, let's say. So those, let's say del L del xi should be equals to 0. So from this, if you do this for this Lagrangian function, then what you will get, I have done that, so I'll directly write that. Okay, so it will be
Minus 14x minus 6.
okay, minus 14x minus 6 plus lambda 1 plus lambda 2 equals to 0, right? So from this you will get x is equals to lambda 1 plus lambda 2 minus 6 by 14, right? I don't have place for this. Wait, I'll put,
Minus 14.
yeah, minus, wait, I'll put one more slide here so that shit, oh fine. What is happening? Okay, okay, minus lambda 1 minus lambda 2 plus 6 by minus 14. So I did
This is
minus,
correct only.
yeah,
Yes, this
correct,
is correct.
yeah. And then this one was 1, second one was del L, there will be options here, so I will not write here. Wait. So second one was del L del y is equals to 0, let's say. So y, with y I meaning yj. Okay, so from there, if you solve, just solve that, you'll get this as 2 lambda 1 minus 3 lambda 2 by 10. This by, sorry, 10, right? Then okay, I'll do in the next page. Third one was del L del lambda 1 should be equals to 0. So from this you'll get another equation, that is x plus 2y minus 10 plus y1 square is equals to 0. So fourth one will be del lambda 2 equals to 0. With this you will get x minus 3y minus 9 plus y2 square equals 0. And we have more. Did I do some mistake or something? Okay, so this one was x, I meant x. Okay, because we have two variables x and y. So these two are, if you write x1 x2 x3 x4, these are del x del xi. Okay, these are, sorry, I not write this side. So these are, where should I write? These are del l del lambda j. Then we have to write del l del lambda, sorry, y1. This y1, okay, so y is mixed. So this y means only the y of the variable that is given, and here y1 y2 means the new terms that we have introduced. Okay, this this equals 0. That is, from this you'll get 2 lambda 1 yj, sorry, y1 y1, what is happening, equals to 0. And we have one more, that is del 2 equals 0. With this you will get 2 lambda 2 y2 should be equals to 0. Okay, so now solving this with all the cases, so from here you can have, so let me write the equation number. Let's say this is equation 1, this is equation 2, this is equation 3, this is equation 4, this is equation 5, and this is 6. Now from equation 5 and 6, what we can write, either lambda 1 can be 0 or y1 can be 0, then lambda 2 can be 0 or y2 can be 0. So you can just assume two cases, right? So you can just, let's say for first iteration we'll just assume this lambda 1 equals to 0 and lambda 2 equals to 0. Okay, now with this lambda 1 and lambda 2, you can just solve this, all this and all. So from there you will get x is equals to minus 3 by 7 and y equals to 0. Now if we put this x and y value in the function, that is z dash, or let's say whatever we have written, so z dash will be what, z dash was what, minus 7x
Sir,
square. Yes, yes, minus
sir,
7.
could you please go back to the previous slide?
Yes,
X, X values I want to need. X equation. Previous slide.
before this.
Yes, sir. X lambda 1, lambda 2. Okay, sir. Okay. Minus 3 by 7.
Correct only, right?
Y is, yes.
So minus 6x, what was that, minus 5y square, minus 5y square. So if we put x and y value here, what you will get, I think you'll get 9 by 7.
Sir, but X and X must be greater than 0. It is the condition given. X must be positive.
Yeah, yeah, I'll come to that. So here what we are getting, that if we go by this way, then minimization of z is coming as 9 by 7. So then z will become minus 9 by 7 because it is maximization function. First of all, this x should be greater than equals to 0, so we can't take this, right? So we can't take this value, so we have to get to the next case. So this one was the case when lambda 1 equals to 0 and lambda 2 equals to 0. Now we'll consider, if let's say case 2, let's say if I'm writing when y1 equals to 0 and y2 equals to 0, right? So in that case, if you solve whatever you are getting, so let me solve that. If I put that, then it will, this equation 3 will become x plus 2y minus 10 equals 0, and equation 4 will become
X minus
x
3y
minus
equals
3y
to 9.
minus 9 equals to 0, or whatever. Okay, if you write like that. And from equation 1, what was the equation 1? Okay, So with equation 1, what will you get? We'll get x is equals to, so okay, I'll directly write, otherwise it will take time. So if you take this equation 1 and equation 2 and the equation 3 and 4 that we have written just now and just solve, then you'll get lambda 1 and lambda 2, how much it will be. Let me see. Wait, I have did that. Yeah, so you'll get lambda 1 as 84.6 and lambda 2 as 57.76, correct?
From these two equations, we are getting
No,
x and y.
so from 5 and 6 we got y1 equals to 0 and y2 equals to 0. Now we
Yes.
put this y1 and y2 in equation 3 and 4, that is whatever we have got now.
Yes,
That
sir. We are getting two simultaneous equations solving x and y. We are
solving
substituting.
equation this two 3 and 4, you will get x and y. Now using that, if you put here in equation 1 and 2, you will get again two simultaneous
Okay.
equation, and from there,
Lambda 1 and
yeah,
okay,
from
sir.
there you can
Okay.
get lambda 1 and lambda 2. You want the value of x and y? I did it in very rough work and also
Okay, sir. Okay, sir. No
okay.
problem.
So it you'll get lambda 1 and lambda 2 as these values. You can see the screen, right? What is happening? Okay. Something is happening with this. What you can see now?
That question page.
Okay.
Consider the following.
Okay. So it's lagging, I think.
Now it's second page.
Now it's
Do
now it's second page.
three.
Okay. Okay. Fine. Fine. Fine.
Yes.
So now what we have, we'll get the z dash. Z dash what was? Z dash was minus 7x square minus 6x minus 5y. Okay. So if you use those values, so okay. So x is, okay, I'll write that. X was 48 by 5 and y was 1 by 5. Okay, so if you solve that, you'll get minus 702.9. Now anyway, we have transformed z to z dash, so we have to again transform back because the question was z. So z is equals to minus of z dash, right? So it will become 702.9. So that one will become the answer. Is it
Here
clear?
we are,
Yeah,
here we are checking the we are stopping to check the conditions because lambda 1 and lambda 2 are positive.
positive, correct. Okay.
So we don't need to go for further case checking.
Yeah, correct. Because see, what all conditions were there. So in these three conditions that we have kept here, where is that? First one, this del xi equals to 0 we have put, right? Second one was del lambda I, sorry, lambda j should be equals to 0. So that is 3 and 4. Next is this 5 and 6 is what? Nothing but del yj is equals to 0. Okay, one more will come, that is lambda I or lambda j should be greater than equals to 0. So anyway we are getting lambda 1 and lambda 2 as greater than equals to 0. In the previous case also, the case where I have assumed lambda 1 and lambda 2 as 0, in that case our x is coming as negative, so we can't take that. But that is also one case, because that is what condition we have lambda j should be greater than or equal to 0. So that can also be the case, just in because we are not getting the x as greater than 0, so that's why we can't take that case, right? So from this case too we will get 702.9. So this one will be the answer. Okay, fine. So answer will be this A, right? Okay, let's move on to the next question. Using the Kuhn-Tucker conditions to solve the, okay, use the Kuhn-Tucker conditions to solve the following problem. That is maximize x y, that is the function subjected to x plus y square is less than equals to 2. Okay, so this same question will be there for the next two MCQs. So first question is choose the correct statement. Just I'll just see this question so that you can just note it down if you are doing that. So let's say if we are writing this as f of x, where this x is equals to x and y. Okay, so f of x will become xy and from this, let's say if you are writing that, we can write gx, because we have only one constant, I'm not writing g1 g2 and all. This one will become x plus y square, sorry x square nahi, what happened, hmm. X plus y square minus 2 plus y1 square. This y1 is the extra term that we have introduced. Okay, now again, what they are saying, anyway the next two problems will require the global optimum and all, so you have to again solve the way we have solved just now. So what we have three, first those necessary conditions, that is here only we have del L del x should be equals to 0, that is x के साथ में y will only come. Oh, L you have to write first, right? Okay, L I'll write. Let's say I'm writing L here. L is equals to what? L equals to xy, that is f of x, plus lambda 1, only one constraint, so only one lambda will come. Lambda 1 into gx, that is x plus y
X
square
plus y square
minus
minus
2
2
plus y1 square.
plus y1 square.
Okay, now if we do this x के साथ, it will come y plus x के साथ और कुछ नहीं है, lambda 1 equals to 0, and then del L del y is equals to 0. With that we'll get x plus 2y lambda 1, 2 can khatam, and this is also 0, so this one will become 0. Okay, so these two are which condition? These two are del L del xi equals to 0, right? Next what we have to do del L del lambda j equals to 0. So from there we can write del L del lambda 1 equals to 0, right? So how much you will get lambda 1 के साथ?
X
So
plus y
simply
square
x plus y
minus
square
2
minus 2 plus y1 square
plus y1 square.
equals to 0. Oh, lambda 2 we don't have, so it's fine. Okay, and next one will be del L with the new term that we have introduced, right? So this means what? Del L del y1 equals to 0, that is how much will come? 2 lambda 1,
2y1 lambda 1.
yeah, 2 lambda 1 y1 equals 0, correct? So again, how we have four equations. This, let's say you are writing this as 1 2 3 and 4. Okay, can you just solve this and tell me what you are getting in what case and all? So here you can only assume two cases, that is either lambda 1 equals to 0 one case, and y1 equals to 0 one case. I'll drink some water. Okay, so let's say case 1, if I am writing from the equation 4, what we can write, that lambda 1 equals to 0. So if lambda 1 equals to 0, then what will become? This from equation 1 and 2 you will get x as 0 and y equals to 0, right? And if x equals to 0 and y equals to 0, then what we will get? y1 as y1 square equals to 2 root 2.
Sir, sir, how x and y 0 if lambda 1 0?
See, from the equation 4 you can write lambda 1 equals to 0, right? One case.
Okay,
Now
okay,
if you
sir.
put that in equation 1 and 2,
Okay, 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 sir.
then you will get x equals to 0 and y equals to 0. Okay, and y1 equals to root 2, let's say. This you don't need, but just from this case I'll tell you. Okay, so from that what you will get? F of x as 0, right? And in the case 2, let's say if we are doing y1 equals to 0, if we are putting, so in that case what will happen? Y1 equals to 0. Okay, so now,
X plus y is equal to 2.
sorry, x plus y
Y
square
square
equals to 2 or
equal
minus 2, whatever. Okay, minus 2 equals to 0, right? Now from this equation 1 and 2 you can write from, okay, I'll write here. From equation 1 and 2 you can write what? That y equals to lambda minus lambda 1 you can write
Minus
from,
lambda
right?
1.
So from there you can write
Mm.
x is equals to minus 2 lambda 1
No.
into y1 is minus lambda 1. So this one will become 2 lambda 1 square, right? And y1 is, sorry, y is minus lambda 1, right? Got it?
Yes, sir.
Okay.
Y
So
is, yes, sir. Yes, sir.
from there you can write here x is how much? 2 lambda 1 square. Y square will be lambda 1 square equals to 2, let's say. So from there you will get lambda 1 square equals to 2 by 3 and lambda 1 equals to root over
Root
2 by 3,
2
right? And now if you put this lambda 1 there, then what you will get?
x and y in equation 1 and 2.
Yeah,
Y will be minus
but
root
remember
of
this,
the.
when we are doing this it will come as plus minus, right? Because we are rooting that.
Yes, sir.
Hmm.
Yes, sir. Yes.
So in case
If lambda
when lambda 1 is negative
negative.
root 2 by 3, oh, I don't have space, I'll write here, or I'll write here, okay, in here. So let's say when lambda 1 is minus root 2 by 3, in that case what will happen? क्या होगा?
Y is plus root 2 by 3.
Y is equals to plus root 2 by 3 and
X.
x equals to 2 by 3 into 2, 4 by 3, right? Right?
No, no, it will be negative because
It's square, right? Lambda 1 square. X is 2 lambda 1 square,
oh,
right? So it
okay,
will
sir.
become 4 by 3. So which condition you think we have to take? Z from the here you can get f of x, that will come later, but case 1 or case 2 we need to take. You need the global maxima, okay, because we are maximizing the function. Now if you write this you'll get how much, something in right, root 2 by 3, something 4 root 2 by 3 root 3, right?
But lambda cannot be negative, na? Lambda must be greater than 0.
Yeah, but that was in the case of minimization. Don't mix everything,
Okay, okay, sir.
right? Here we have not changed the function to minimization. That also I can do, it's not an issue. You will write f of x as minus xy and then you do that same, okay, you'll reach to the
Okay,
same conclusion.
okay,
Okay.
sir.
Yeah,
Sorry,
don't
sir.
mix this kind of thing in exams, otherwise it will be difficult. Okay, so what I was saying, yeah, so here we are having f of x as 4 root 2 by 3 root 3, let's say. And in case of 1 we have f of x equals to 0. Which one need to be considered for global optima? This case 2. Why? Because that is having higher value, we need to maximize the function, right? So in these two, which one is having more value? That is 4 root 2 by 3 root 3, because it is a positive value, it is more than 0, right? So we will consider this fx is equals to 4 root 2 by 3 root 3 as the maximized function value, okay? And at x equals to what? X equals to 4 by 3 and y equals to root 2 by 3, we'll get that. Is it clear?
Yes, sir. Clear, clear.
I hope it is clear to everyone. Okay, next the question was, choose the correct statement, that is the feasible region is bounded, so a global maximum must exist. So here what we are saying, okay, so feasible region and all, yeah. So let's say if we are drawing that, okay, you can just do that. So what all we have, xy can be xy will be something, x equals to y, xy 1 1 1 में आएगा
It's
1, so
surface
it will be
plot.
something like this, I think. If you do the projection, Yeah, correct. It was surface plot. It will be like something like this. Okay. S- okay, whatever. Okay, we'll not go to the diagram then. It will be difficult to understand. Okay, first read the question properly. It's the feasible region is bounded. So what we need to understand that if the feasible region is bounded or unbounded, in that case what will happen? Because the question is what it. Array, why it is not moving? What happened? It got stuck or something. Okay. So what I was saying. So we have the function that is xy, right? And we have a constraint. Now let's say if the feasible region is bounded, in that case what will happen? So any function, let's say, okay, let's say you have one function. Yeah, we can write like that now. So let's say this is x and this is y. We don't have to go for surface here because only x and y are there. So x and y are there, so the function will be something like this. It will not be a surface plot, it will be 2D plot only. So this one will be this xy some function, this function will something be like this, right? Now you have some constraints, right? The constraint is what? X plus y square is less than equals to 2 and x and y should be greater than equals to 0, right?
Sir, how it is not a surface plot, sir? There are f of x, f is a function which contains two variables. So it must be a surface plot. If it is a straight line,
Sorry,
okay,
correct only.
sir. I
So
am already
no,
confused.
sorry. Correct. So let's say we have you consider one 3D plot kind of thing. So we have this x, we have y plane, right? So it will xy, if you plot it will be something like this, right? So if you project that at any plane, it will be something like that, right?
Yes,
So
yes.
just to imagine I am doing one 2D plot, like to
Okay, sir.
understand properly. Okay, it will be a
Okay, sir.
3D plot only, sorry. Okay. uh, so now let's say you have a feasible region, some feasible region, something like this. I'll draw with some other color. What is happening? Hmm. So let's say you have x plus y square. X plus y square कैसा दिखेगा? Some parabolic only, and it should be less than equals to 0, something like this I think, maybe something like this. Okay, so let's say it should be less than equals to how much? 2 or something. Yeah. Okay, so it should be something like this. So this part we have feasible region. Now if the feasible region is bounded as in if this is not given, okay, consider this x and y is not given, this was not given by mistake, I have written like this. I saw, no, this is there. Now if this x and y is bounded, now this feasible region is bounded, okay, and in that case what will happen, whether a global maximum will exist or not with
It will
this problem.
exist. It will come. It will exist because it's a closed region. Feasible region is closed.
Wait, again it got stuck. What you can see? You can see only the first question, right?
Yes, sir. Yes, sir. Question page, not the second graph.
Oh, it got stuck again. I don't know. Oh, okay, wait. Give me a minute, okay? It got out of this.
Sir, what is the software that you are using for when you are writing in pen? It's like
Simply
notebook, right?
PPT only, PowerPoint only I'm writing.
But how that you are writing like a paper?
I'm writing on my iPad, so.
Okay, okay.
Okay, now you can see, right? This
Yes,
choose the
sir.
correct statement. Yeah. Okay. So when the feasible region is bounded, what will happen? A global maximum must exist, right? So correct answer will be A. Moving on to the next question because I have to explain those also. So the global optimum is at which point? This is for the same question that we have seen, and we did this only. How much we got? Something plus. Both are plus only. Yeah, y equals to root 2 by 3, and so correct answer will be B, right? So for this solution is in which slide number? Okay, some. Okay. Okay, so next question. Again it got stuck or what? Okay. Okay, so next question is what is happening? Wait, there is some lag, I'm not sure. Now it's fine. So next question is select the correct option. So options are for penalty method. So I'll first explain little about penalty method and then we'll come back here. Okay. So the next lecture
Sir,
is
we need a detailed explanation about penalty method. I couldn't understand.
okay. Okay, because we have very less time
It's
and we have.
confusing.
Okay, so next was again constraint optimization with inequality constraint and all. So here what we do, we use the penalty function. Now what is this penalty? What is happening here? I don't understand. Okay. Okay, so what we are doing, we are using some penalty function, or you can say penalty method, let's say, whatever you say. So this penalty function, I'll write penalty method only. Penalty method, fine. So now this penalty method can be exterior penalty method, and it can be interior penalty method. What all those I'll come. Next is interior penalty method, fine. Now let's say you have a function. Okay, I'll take the function, same function that sir has used in his paper, I think. This is f of x is equals to x cube minus 10x minus 2x square minus 10. Okay, which was subjected to
Plus
gx
10.
plus 10. Okay, fine.
X
Gx
cube minus 10.
is greater than or equals to 3. It can have any inequality constant, it can have be positive, so you have to minimize this function, right? Now we can write this as x minus 3 should be greater than or equals to 0. So this is again our gx only. Now in penalty function, what we do, if you just plot this function, that is whatever x cube minus 10x, because we have one function, it will be a 2D plot only. So let's say we are plotting that. Okay, it will be something like this, right? I'll just draw whatever he drew. Okay, so now if we don't have any constraint like this gx and all, then the minimum will be here, right? Let's say at 2.5 or something, I'll write 2 1 and all. Okay, but what we have x is greater than or equals to 3. So just if we draw that constraint, it will be something like this. Okay, this is what, this is x and this is y. Okay, y as in f of x. I'll write f of x only. F of x, right? So x greater than equals to 3 means in this direction, right? Okay, so in this one will become the feasible region. Feasible region and all I'm not explaining because we have explained like 2-3 weeks earlier. And
Okay, sir, I understand.
this is infeasible region, right? Now with exterior penalty method, what we mean that we'll go in the infeasible region and try to come back to the global optimum or minimum, let's say here. Okay, so in that what we do, we consider some function which is called as penalty function. Okay, so this penalty function will act as a bound. So let's say your penalty function will not act as a bound. This line only, the constraint will act as a bound or a barrier. Okay, now what will happen, which color is it? Blue. Okay, now let's say what we are doing, we are using some function. You can use any function that you want. Okay, but generally after doing and all, people came like research and scientists and whatever, they came to some function which will fit to what kind of functions you have. So let's say you have any function that you want. Okay, now in that case what will happen, you will get some function like, let's say this. Okay, this can be one function. Okay, at some value of that penalty function. Okay, then if you increase or decrease the value of the function, it can go something like this and then move on, and it can be like something like this. Now this function is moving when the value of that variable whatever we have, if we are changing the value in the penalty function, then the function will be moving, right? And with this barrier that x equals to 3 or whatever constraint we have to stop there, right? Because it is a constraint. So in that case what will happen, as we move towards the constraint and we reach very neighborhood to the constraint, at that time we'll stop, right? And with that we'll tell that okay, in the neighborhood to whatever we have got, we'll get the global optimum. In this case we will have the global minimum value, right? And in the interior penalty method, what we do, we move to the feasible region, and again we'll change the value of the function, or let's say the penalty function, and we'll keep shifting unless and until we reach the this barrier or the constraint, that is x greater than equals to 3 or x equals to 3 line, right? So this penalty function is written in this form. Where is that form? That is f, लिखा हो भाई, क्या हो गया, f x comma r, where r is the penalty parameter. Okay, so we, okay, I'll go through that. F of x plus some r term was there, where r is the, where is that, लिखा क्यों नहीं रहा है, r of, let's say gx, अरे लिखाओ भाई ठीक से. Okay, you can see, right? Yes. So this f of xr is written as f of x plus r into or not into r gx. This r is the penalty parameter. Okay, this r can be different operator, it can act as different operator, it can act as bracket operator, it can act as inverse operator, it can act as log, whatever function you have taken, based on that it will work. And this term is called as penalty term, because we are giving penalty to this function, that is f of x, right? We are not considering fx, but we are considering some we are considering fx but with some penalty. That's why this function is changing. The line that you can see after the red function, this red one is the f of x, right? Now we are changing the function, that's why the value is changing. So this change is because of this penalty term, right? Now this is for when we have inequality constraint. Again, if we have equality constraint also, in that case, let's say if equality constraint, equality constraint is also available, is also present. let's say some function hx is equals to 0, then the function will something like, or maybe you can write it as maybe, okay, so f of x plus r of gx and hx. Okay, so again this r term is the penalty parameter and the whole term is called the penalty term, right? So this penalty term can be of mm, like different, for different functions. You can have parabolic. Here whatever we are doing here is the in the figure whatever I have shown is the parabolic penalty, because the whole shape every time is parabolic only. Okay, so I have considered parabolic penalty. Okay, so there can be different kind of penalties. I'll write it here. So these penalty terms can be parabolic penalty, whatever I have shown in the figure. It can be log penalty, it can be inverse. So based on whatever you are doing, as I said, you can take any kind of function as penalty function. Okay, so that your work, that whatever you are doing should be you go it should be easier for you. Okay, so based on that you will take these penalty terms. It can be inverse penalty, it can be bracket operator. So what is this bracket operator? So in parabolic you will consider one parabolic term, let's say some r of hx. In logarithm you will consider logarithm, so let's say it will be r of ln of gx. Okay, so this logarithm term is there. Okay, for this, for inverse you will just write 1 by gx, or bracket you will write r of bracket of gx. Okay, so this bracket terms means what? This I think he has explained. So this bracket term, let's say whenever you are minimizing the function, it will be something like, bracket term will tell you minimization of
Sorry.
minimization of where I was writing. So minimization of g of x, let's say, or 0. Okay, but when we have maximization function, then this bracket operator again will become maximization of gx or 0. Okay, based on whatever function you have, you need to consider the bracket operator. If it is minimization function, you have to write the bracket operator such that it is minimum value of the constant gx and 0, whereas bracket operator for maximization function will be max of gx and 0. Okay, so I hope you got the funda. Okay, so is it clear the function, or do you have any doubt? You can ask. I can explain that part then.
Only that bracket operator.
Oh, bracket operator. Okay,
Only.
so let's say what as I said in the function, let's say the the optimization problem is minimization kind. Okay, so let's say minimize fx. Okay, now in that case, if you are using this bracket operator gx, okay, so let's say I will take some value so that it is easy for you. So let's say there is some function gx is equals to mm, x1 plus x2 minus 5. This is also from his ppt only, I think. Okay, now at different x1 and x2 value you'll keep doing that, right? Now as we are the objective function is minimization type, so this bracket operator will mean minimization of gx and 0. Okay, so let's say at, for let's say I'm assuming x1 as maybe what one, 3 and 3. Okay, something like that. X1 and x2 is 3 and 3. So in that case, this rgx or the bracket operator, what it will mean? It will mean minimization, minimum value of g of x1 x2, that is 3 comma 3 and 0. So it will be how much? Gx will be 3 plus 3 6 minus 5 1, right? So it will be one minimum of 1 and 0, that is 0. But again, if the function of the objective function changes to maximization of that of f of x, then what you have to do, this bracket operator will change to maximization of gx and 0. In that case you have to consider maximization of 1 and 0, that is 1.
1. Okay.
Clear?
Clear, sir.
Okay,
Clear.
fine, we'll move to the question. Where we were here, I think आंसर कैसे भी दिख जाता है. Okay, so in this case, interior penalty method and all I told, right? Select the correct option. In case of interior penalty method, we penalize the solution in the feasible region. In case of exterior penalty method, we penalize the solution in any region. In case of interior, okay, you just read and can you just tell me what will be the answer? Just now we have discussed this. This is simple only. In interior penalty method, remember, whenever we are doing saying interior, this means we are working with feasible region. When we are saying exterior, this means out of the feasible region, that is infeasible region. Okay, so in this the correct answer will be A. Is it clear?
A.
Okay.
Yes, sir.
So if it is mentioned here, select the correct options and you just see if it can be more than one options also. Okay.
Okay, sir.
Again, it is not coming in the Gmeet. It's coming. Okay, so what I said, ki if you can see this options, then it can be more than one option also. Okay, or it can be one option also. It's not like it will have more than one option. Okay, next question. Considering following two questions, the interior penalty term is initially set at small value and then increased to larger value at later iterations. Okay, this I have not explained. I will tell you once. Okay, so I was explaining this, right? In this figure you see. Okay, in this figure what we have seen, that the red one is the main function, that is f of x, that is given as the optimization problem. Now we are doing some penalty term in the infeasible region as well as in the feasible region. So same thing you will do in the feasible region also, and you will get to the constraint. Okay, now so let's say in case of exterior penalty method, what we do, we consider a very what you should consider. Let's say if you have in exterior penalty method in infeasible region, if you are there, then what will you consider? First you will consider as, like, can you just tell me how should you move?
What's the constraint?
Sorry, constraint
From the
is
left side,
from,
from the left side towards the constraint,
yeah,
we will move.
we'll move like that. But I'm telling about the penalty term or the penalty parameter, let's say. So what should be the value at the farthest one in the infeasible region when we are doing about exterior penalty method? Forget the interior penalty method for now. So when we are in exterior penalty method, that is we are in the infeasible region. Okay, now if we are at the farthest, okay, you just consider this function only, penalty function that we have written, f of x r is equals to f of x plus r of gx, right? And gx is what? X minus 3. Okay, now if we have a bracket operator of x minus 3, okay, and you are considering r as a very, let's say, very low value, then what it will become?
Negative. That bracket of
It will come as
AB.
0 only, because it is a minimization, minimum value of x minus 3 and 0, remember here, because gx was x minus 3, so it will be minimum of gx comma 0. So it will come at as 0 only, the operator. But what should we take? R as, when we are in the farthest side, then the R should come from which side? I mean, it should be higher or it should be lower? I'm not sure if it is. Sorry. So what here, what whatever I'm asking is the same question. So what I'm saying in the question 2, in this statement 2, if you see, the exterior penalty term is initially set at large value. So as I said, what we have to do, we have to keep moving. If we just directly take one a large value, okay, so if you take a very large value, it will directly reach to the global optimum. It is not the case, because if you directly take a larger value, we are anyway, we are going in the gradient direction. Okay, so we are moving as so let's say if you have a minimization function, okay, so what you will do, we'll go to the minimization side. So it should be descent direction, not the ascent direction, right? So we have to move slowly so that we can reach to the minimum. So if you directly consider a very large value, then what will happen, it will have a very decent steep, a very steep descent. Okay, so because of that, we can't use this gradient descent method. So for that, we have to take small steps. So that's why what we have to do, we have to first in the exterior penalty method, you will consider a very large value of r, then you will keep reducing that. So let's say if you are considering r as 10, okay, then 10, 9, 8, 7, 6, 5, 4, 3, so you will reach till 0, let's say. Okay, so in if you reach pakka at 0, then you will reach at the minimum point. So you can't reach at 0, so you'll maybe 0.01 or whatever residual you are considering. Okay, so in exterior penalty term, the initially it will be set at very large value, and then slowly you will come to less value of the penalty term. Okay, and then okay, it is written here. See, the exterior penalty term is initially set at large value. Similarly, the interior penalty term will be set at small value, and then it will increase to a larger value at later iterations. So both these are true only. Okay, so okay, so I oh wait, sorry, yeah, okay, I'll do that here. So let's say you have a function, I'll create that x, and this is f of x, right? You have something like this, okay, and you have one constraint here. Let's say this is 3, and you have a constraint gx as x minus 3 should be less than equals to, sorry, should be greater than equals to 0. Okay, so this one will become infeasible region, and this one will become feasible region. So in the infeasible region, we'll do the exterior penalty term. Now if you take some color, so what I'm doing, I'm considering one function, so that it should be something like this. Okay, then again you'll change the value of the, what to say, the penalty term, and then it will be something like this, right? So this one will be, let's say r equals to 0, then you will consider r equals to 1, and like that you will keep continuing. Okay, so when r is a very large value, maybe let's say here something like this, so here it might be something like maybe 10 or 100, something like that. At very large value of r, you will reach to the constraint or the binding wherever we are having the barrier. Okay, similarly in the case of interior penalty term, it is opposite. This means what, there is some function, let's say something like this. Okay, so see, this is one kind of function only. So this is for r equals to a very high value, let's say maybe in this case we have a small region, so I'm considering 2 as a very high, or maybe 2 as a very high value. Okay, now if you reduce this, then the function will be something like this. Okay, in the next case, so this will be r equals to, let's say 1.5. so you have to keep reducing that so that you can reach the barrier where we have the global optimum. In this case, we have global minimum. Okay, so you have to minimize this function, minimize fx, right? So what is mentioned here, that interior penalty term is initially set at small values, but here this is the place where we need to do the interior penalty method, right? So in this case, you have to start with a larger value and then keep reducing that. Okay, and in exterior penalty term, you have to take one small value and you have to keep increasing that. Okay, I hope it's clear with everyone. Okay, I'll consider it. It's clear, right?
Yes, sir. Clear, clear.
Okay, okay. I hope it's clear with everyone. Okay, so the correct answer will be D. Okay, so in this case, in first case, what should be the answer? It should be a larger value, and it should decrease with as you move with iterations. And in this case, it should be a smaller value, and it should increase with uh, iterations. Okay. Okay. So next question is, consider the optimization problem given
Sir,
below.
sir,
Sorry.
could you please go back to the previous slide?
Yeah.
Let me note it.
I'll give this slide. We have less time. We have to finish.
Okay, okay, sir. Then okay.
Okay. Consider the optimization problem given below. Okay. So the problem is simply minimize f of x subjected to g of x is less than 0. Where is the question? Shit, man. Oh no, no question is not needed. Fine. No question should be there. Oh shit. Gx. Give me a minute. I have not written the question for this. I think this is bracket operator only. Yeah, yeah. So the question is, if we are considering this optimization problem, then you are considering a penalty function of bracket operator. Okay. So this means what? That bracket of gx. Okay. So this means what in this? That is what question is. Did you understand the question?
Yes, sir.
Okay.
Yes, sir.
Yeah. So you just need to tell me the which one will be the correct meaning to this bracket operator of gx. Remember that we are considering minimization of fx as the optimization problem. Just now I have explained this.
Option A.
Option A. If gx is greater than 0, it should be gx, and if it is less than equals to 0, then it is 0. Correct. So this just now we have explained that this means what? This means minimization of gx and 0 only when we have the optimization problem as minimization function. Okay, so let's say whenever we have gx is greater than equals to 0, then what it will become? Oh wait, there is some issue. Okay, so the function here is only gx is less than equals to 0. Okay, now let's say I'll take an example only. So let's say if those that the function was there, no, gx was what was that, x minus 3, x minus 3 is x is greater than equals to 3. This one was the problem, right? So we can write this as x minus 3 as greater than equals to 0, right? Now if we want to put this, that is gx bracket, then what we can write? So this gx will be 0 when, see, you have this right here. Now if gx is or x is greater than equals to 3, in that case what will happen? This will be 0. Otherwise what will happen? The penalty function was what? F of xr is equals to f of x plus penalty term, that is gx. Let's say here bracket we are putting, right? Now if after moving ahead from the x, that is x equals to 3, say we move to the right hand side, that is x greater than equals to 3, and if we consider some value to that, then what will happen? Then it should become 0. Otherwise it will keep increasing, right? Did you get my point? See, let's say if x equals to 3 is there. Okay, now you are saying at x greater than 3 we are putting some value to it, right? In that case what will happen? This function, that is the penalty function, will keep increasing as you move away from x equals to 3, x greater than 3, right? So in that case we have a minimization function. If we keep moving and if we are keeping putting a value to this penalty function, then it will become a very large number. Okay, so this means that is not the case. So when x is greater than equals to 3, the penalty term should be 0, right? And when we have x less than 3, which is in the infeasible region, in that case what will it will become, it will become the constraint, right? Because after constraint, if you move and if you reduce that, then what will become, it will become infeasible region. So in that case it should be gx, gx, right? This bracket operator. Okay, I hope you got it.
Yes, sir.
Clear, right? So from for this problem, that is minimization of f of x subjected to jx less than equals to 0, correct option will be a only. So this I have just explained so that you can understand it properly. Okay, let's move on to the next question. Question was there, the output of the bracket operator will be, okay, why did I write then? Fine, I'll rub this. Okay, next question is select the correct option. The penalty function method and augmented Lagrangian multiplier method are called transformation methods, because we are transforming this penalty function method and, okay, augmented Lagrangian multiplier method. Okay, that is also a function only. Okay, it was something like f of x plus some constant c1 by 2 into some function will come and c2 by 2 some function will come. I'm not going into that because he has not explained all that. Okay, so this augmented Lagrangian multiplier method and penalty function method both are transformation methods only. Okay, next is in penalty function method, a large value of penalty parameter may make the Hessian matrix of the transformed unconstrained function ill-defined. Okay, okay, what is that? Penalty function method, a large value of penalty parameter may make. So let's say just now I mentioned कि if the penalty parameter is getting values much bigger than that. This is in the case of a minimization type. Okay, when if it is not mentioned maximization, this means we are considering minimization in this problem, whatever is there. Okay, so in penalty function method, if we are keeping a large value to the penalty parameter, then the Hessian matrix for the sufficient condition, it will be a ill-defined problem. So this is also,
Which means that steep descent you
yeah,
said.
steep descent will come because
For that case, Hessian matrix cannot be defined. Is it so?
now it can be defined,
In
but it will not be well
ill
defined.
defined.
Yeah, it will not be well defined. Okay, so the correct option
Then
will be C. Okay, I'll move that. Again, we have one question, that is, what is the time? Time we have. Okay, fine. Consider the following optimization problem, that is minimize f as minus x1 x2. So this is the function subjected to two inequality constraint, that is g1 as x1 plus x2 square minus 1 is less than equals to 0, and g2 as minus x1 minus x2 is less than equals to 0. Okay, so the question is the composite function will be, so this r here, small r, is also same penalty term only, or sorry, penalty parameter only. This penalty parameter in different books they will consider as different. Someone will write r, someone write small r, someone will write as barrier function also, b of x, something like that. Okay, so the composite function will be, how we can write, we have defined that. See here, so here what I have mentioned, that the composite function is this function only, that is f of x r is equals to f of x plus the penalty parameter. Okay, this function, that f of x r is the composite function here. Okay, so with that only, so it is, what should be the composite function, f of x r, if we write in our way, it should be f of x plus r of gx, or here we have two functions, I think, g1x and g2x, so we'll write as r of g1x, it was capital chota g1x plus r2 into g2x. Is it clear? With this we'll come
yes,
to
sir.
this.
Yes,
Okay,
sir.
now here we have small r, so we'll write as txr as fx is what, minus x1 x2 plus, see in the question it is mentioned as, okay, so it is कुछ तो गड़बड़ हो गया है, wait, let me check, minimization, Yeah, okay, okay, fine. Something mistake I did or something. What? Let me check once. It is minimization function only. Okay, I think I have done problem in the question. Give me 1 minute. Let me recheck the question. Yeah. -1 square bracket over it to square. Okay. So this bracket was 1 square was there. Okay, I have not mentioned that there, I think. Yeah, so this bracket meant square of this. Fine. This bracket of gx will be minimization of gx comma 0 its square.
Okay, sir.
Okay, so this one will become square, it will come as
Sir,
0.
this is a regular format or for this
No, no,
question?
it's not like that. It again, as I said, it again depends on whoever is working with it. So in different, yeah, different
Voice
books,
was
different books you will get
your
different.
voice was breaking.
Sorry, hello.
Your voice was breaking. Now you can tell
Okay, okay.
what
So
did
what
you
I
do.
said, ki in different books you'll find different like in this operator only. As I said, here I mentioned, right, this bracket only. Somewhere you'll get it as minimization of gx and this square, and somewhere it has maximization of gx comma 0 square. So sometimes it's very confusing what to use when. One is when it is minimization of fx, you can keep minimization of this. Okay, when one is maximization of this, you'll get maximization of this gx comma 0 square. Okay, but in the problem that I have given, this is the same problem I think from the quiz from yours, I think, but they have taken from one book, I think, so it will be first one only. Okay, it I'll go to it this one. You can't see this. That now you can see, I think. You can see the composite function, that slide, right?
Yes, sir.
Okay, okay, fine. Yeah, so for this it will be r of max 0 x1 plus x2 square minus 1 this square plus there is some confusion in this. Okay, this I will see once again. Okay, because I am also confused somewhat in this. Okay, for now this one will be the answer A, but as we have discussed, it should be D, right?
Yes, sir.
This I'll
Yes,
see
sir. I
once.
also thought of D,
Mm-hmm.
but you are
Yeah,
telling
yeah. Uh,
A.
if it is there in this quiz, for now you attempt A. Fine. I'll
Okay, sir.
go through this once again, and I'll tell you where to keep what. Okay.
Okay, sir.
Okay, fine. Next question is so the same question. Okay, the same function, objective function, and the constraints. Comparing the derivative of composite function, that is this function, with KKT optimality conditions. Okay, so optimality condition is del L del X is equals to del F del X plus lambda 1 del G 1 del X. All that the Lagrangians multiplier, that is lambda and 1 and lambda 2, you have to get. So you just need to get this transformation. Sorry, the composite function anyway we have did, right? You just need to get the ah why this is happening. Wait. Sorry, I don't know why this is happening again and again. You can see the screen?
Yes, sir.
Okay, sorry. Okay, where it was. Yeah, so what I have to do, we have to get the derivative of the composite function. This function, this is the composite function, right? So just get the derivative for both the x1 and x2. Okay, and just tell me what you are getting, or I will only write directly. So del t del x1 will be what? That was minus x1 x2. So with x2 x1 you will get x2 plus 2 into that r function. Okay, I think that is because of the small r and capital R. Okay, I'll check that. R of likha ja bro max of 0 comma x1 square, what was that, x1 plus x2 square minus 1 whole square. So whole square से आया मेरा 2, right, plus 2 into that r value of maximization of 0 comma, what was the second constraint, x1 minus x1 minus x2 minus x1 minus x2, this one, right? Similarly you will get do we have space here? Yes, del t del x2 as minus x1 plus 2 into r maximization of 0 comma x1 plus x2 square minus 1 plus 2r maximization 0 comma minus x1 minus x2. Okay,
Sir,
yes.
sir, Lagrange multiplier method
No, not
and
method
this
here. Here we
penalty
are,
function method.
no, here we are not doing Lagrange's multiplier method. Anyway, this that del L del X whatever it is
Why should
written.
we club both? Why both are clubbed here in this question? Combined Lagrange method and
Yeah,
penalty
that is
function
no.
both
The question is that only that we are comparing both. We'll come to that. Why
already.
already? Sorry.
Okay, sir. Already inter penalty method is confusing in this Lagrange also included.
Okay. So what we'll do? We'll take that Lagrangian function because every function
Okay.
is every method is doing the
Sir,
same work.
we are
Ananga.
applying the Lagrange method in that composite function, right?
No. Lagrangian method is Lagrangian method. Composite method is composite method. We'll just compare both the functions with this function. See,
No, sir.
one function is this del L del X, right?
Okay, sir.
One
Okay, sir.
function is this del T del X, where T is the composite function from penalty method.
Okay.
Now we'll compare
Okay.
both this del L del X and del T del X,
Okay, sir.
and from there we'll get this Lagrange's multiplier. Okay.
From del t, we are getting the Lagrange multiplier.
Yeah. See, so we have del T del X here, del T del X1 and del T del X2, right?
Okay. Oh, yes, sir.
Okay.
From that, we are getting the Lagrange multiplier.
From there also we'll get one function, or you can say one expression, which will be very similar to this function, that is del L del X is equals to del F del X plus
Okay.
lambda 1 del G1 del X and plus lambda 2 del G2 del X. From there we just need to compare, like in kid when we were writing, let's say 5a plus 3b equals xa plus yb. Okay, so from this what you can say, x as what and y as what? X as
X is 5,
5
Y
and y
is
as 3.
3.
Same thing we'll do here.
Yes. Okay, sir.
Okay. Yeah, where I was. Okay, is it clear that how we got
Okay,
this
okay.
del t del x?
Lambda 1 is what? Yes, yes,
Yes,
yes.
yes, yes. That
Now
is what
lambda 1 is okay.
that we have to find out. We don't have to do any
Okay, sir.
methods here.
Just replacing.
Just
Okay.
that's it. Okay.
Okay, sir.
Okay, fine.
Okay, sir. So please share the slides today itself, sir.
Yeah,
I
yeah,
will.
I'll share.
Okay, sir.
Where I was. Okay, now you have to find out this. This you have to find out. Just small things. This you have to find out because this del g del x and all you have to find out. So del f del x will be what? What is del f del x? What was the function? I forgot. Minus x1 x2. Okay.
Minus x1, x2.
Yeah. So del f del x1 will be minus x2. Del f del x2 will be minus x1, right?
Okay. Okay, sir.
And then del g del x del g1 del x1. I'll directly write del l del x only. Otherwise, it would, so many things are there. Okay. So our del l del x1 will become what? Minus x2 plus lambda 1 into del g1 del x1, right?
Yes, sir. Yes, sir.
Yeah. So it will become del g1 del x1 plus lambda 2 into del g2 del x2, right? Now here g1 is what? G1, can you just tell me how much? Oh, you have not
Yes.
written, right? Did you write? G1 is,
G1 is
do it here only.
x.
Wait, del g1 del x1 is 1. That's it. Del g1 del x2 is minus 1. Sorry. Del
2x2.
g2 into x2
X2.
del g2 del x2
Mine.
del g2 del x2 minus 1 del g2 del x, eh, okay, I did ऊपर नीचे थोड़ा, x1 minus 1 only, right?
Yes.
Oh my god. Okay, whatever. Okay. Okay, so put that here. It will be minus x2 plus lambda 1 into del g del x1 was how much? Have you written that, or I'll check. Del g del x1 was 1. Fine.
Mm.
So del g del x1 was 1 plus lambda 2 into del g2 del x2 how much?
Del G2, del X1 or del X2?
Sorry,
Del
del
X1
x1
means
1
minus
del x1
minus 1. Minus 1.
minus 1. Okay, so what we are
Yes.
getting, and and
Del
so this one
del
will be
G1,
compared,
del X2.
this one will be compared with this one. Okay, so this one we have found out just now. This is minus x2 plus 2r of this plus 2r of this, right? So with that, if we compare these two, lambda 1 is how much? Just compare.
Okay.
Okay, I'll write properly.
2 are max of 0, comma x plus x2 square minus 1.
This equation, equation 3, this is equation 2, this is equation 1. So what we are doing, comparing 1 and 3, right? Yeah.
Okay, sir.
Lambda 1 is how much?
Lambda 1 is 2 are max of 0, comma x1 plus x2 square minus 1.
I,
So option A can be.
and lambda
Then
2
we
is
have
how
to check
much?
for lambda 2.
Lambda 2. Here minus 1 is there,
Lambda
okay?
2, I have to write.
So
Where, sir? Yes, sir. Yes, sir. Minus 1. x1. So minus 2 are max of 0 comma minus x1 minus x2. Minus 2 r is not coming.
Wait, wait, wait. Yeah, in this here I did some mistake, I think. Here I was doing with x1, right? So इसका x1 के साथ it will come
Yes,
as
sir.
1 only,
x2 we
and
have to.
no, here also it x1 will come something, um, del
Okay.
minus 1. यहाँ पे minus 1 will come. See, minus x1 minus x2 again it should be derivated. So what I did, see, I'll tell. Don't get confused, okay? See this term. I did this
Yes, sir.
with I did the I took the derivative of this term with what,
Mm.
x1, right? So
Okay,
this
sir.
this
Okay,
became
sir.
2r. This is because of this square term, 2r of max 0 comma minus x1 minus x2, this, right? Now you have to take derivative of this also, so with that you will get minus 1. Okay, clear?
Yes.
Okay,
Yes, sir. Yes.
yeah, so by that way here also minus 1 will come. Now you tell me how, what will be the lambda 2 value. It will be
Then positive 2 r
yeah,
max of
max
0 comma
0
minus
comma
1
minus x1 minus x2, that's it.
minus x1 minus
Now
x2.
if you do same thing, like if you do del L del x2 and compare it with del t del x2, you'll get the same result.
Yes, sir.
Okay, so correct answer will be A, right?
Yes, sir. Option A.
Clear? Here we are not doing any methods and all, you're just
2
comparing
r
and then
max.
getting, that's it.
Compare. Okay, sir.
Clear, right?
Clear, sir. Clear.
Okay, fine. Yeah, done. We went very out of time. Fine. Everything is clear, right? Is there any question? Anyone? Okay, if not, I'll stop it here only. Okay, and I'll check that max thing. I think that is because of the small r operator. Okay, if that is there in this quiz, you just apply max. Fine.
Okay,
Okay.
sir.
Okay.
Sir, please remember remind that team for week 5
Okay. Okay.
error in the options.
Yeah, yeah. I'll check that. I mean,
Sir,
I'll inform them. I'm not sure who is
sir, I
handling
need
that
that.
also. I'll do that. First, I have to
Okay, sir.